So it's a great pleasure for me to welcome our next speaker, Pierre Fraignaud. Pierre is directeur de recherche au CNRS in France. So France has this distinction between CNRS, INRIA, research centers and university. Maybe it's again something that dates back to Napoleon, I don't know. But it will probably disappear. So Pierre is directeur de recherche in CNRS. CNRS is Centre National de Recherche Scientifique. I think 20,000 people. Among those 20,000 people, there are very, very, very few every year who get a medal. And Pierre Fraignaud is one of them, médaillé du CNRS. Je suggère qu'on l'applaudisse avant même qu'il fasse son exposé. Pierre studied in Grenoble and got his PhD at École Normale de Lyon, and he has been directing the LRI, Laboratoire de Recherche en Informatique, in Paris-Saclay. Is that correct? Almost correct. So I give him the floor, so please quickly come and sit and don't miss Pierre's talk, who will explain to you everything you wanted to know about what a network is.
Thank you, Rachid. Okay, thank you very much. I need the little button. Here it is, the button. I guess it's this. Yes. Okay, so thank you very much. Thank you, Rachid, for the introduction. Just one comment. It's not Napoleon who created CNRS. It's due to Charles de Gaulle. So you see it's this type of, our two main guys are showing up in this conference. What I want to do today, I want just to tell you a little bit about the notion of locality in distributed computing and the fact that locality has very different aspects. And it's not only a notion of distance between individuals or between processes or between whatever is computing in a system, but it can be viewed from different perspectives. So, but before doing this, as opposed to what was said in the morning, I hope it will not be technical. We will mostly do a game during this presentation. So, locality, as you know, it's the notion of time and space, how long it takes for an information to come from one place to another. So let's say from the red points here to the blue points. And of course, in physics, we are limited by the speed of light, so it will take a certain time until the information reaches the blue point. In distributed system, there is also this notion of locality. It could be physical. So for instance, here on the left, top left, it's internet. Here it's a data center, and there is a notion of locality. But also in your computer, usually computers are multi-cores, so you have many little processors that compose together one chip and one computing unit in your computer. And also here we have some notion of locality that I will mention a little bit at the end of the talk. But to start with, I want to do a little game to show you that locality is a subtle notion. And then we will come up later with this problem of locality, even in system when there is no notion of distances. Okay, so here is the game. I named this game as the Moroccan restaurant game. So it's a very, very simple game. It's a game between two players, and you can play this game next time you go to a restaurant with your husband, your wife, your friend, whatever, you must be 2 people. So in this restaurant, the owner of the restaurant offers you the meal if you win the game. So there is no point of refusing playing the game, apart from the fact that you will be seated by yourself and not with your companion. So for instance, here there is Amina and Basim. They came to the restaurant, and they are seated in 2 different places in the restaurant, far away from each other. And not only that, they are separated by a wall. They cannot communicate at all between them. And of course, the cellular phones are forbidden. I mean, no way you can communicate. So they are at 2 different parts. Now, in this restaurant, there is a particularity that there is no menu, but the waiter comes and offers and proposes you something. And then, depending on what the waiter proposes, you may accept or reject, or you may accept the meal or take another meal. So essentially, the waiter here proposes either tagine or couscous. So what does it mean? It means that to each of the 2 players here, Amina and Basim, the waiter will come, and for instance, will come to Amina and say, okay, I offer you tagine. And then the waiter will come to Basim and say, I offer you couscous. And then the players, Amina and Basim, they may accept or not the proposal, which means that if Amina is proposed tagine, she may take the tagine, or she may say, no, I take the couscous. And same thing for Basim. Now, the point is that there is a strict rule on what should be the choices of Amina and Basim. And the rule is as follows. So we have to take a little bit of time to understand this rule. It looks stupid, but let's focus a little bit. If Amina and Basim are both proposed the same meal, and actually in this case, couscous. If Amina and Basim are both proposed couscous by the waiter, again, the waiter came to Amina and to Basim separately. He proposed, so if the waiter proposed to Amina couscous and also proposed to Basim couscous, then one and only one of them should accept the couscous, and the other one should take the tagine. It doesn't matter if it's Amina who takes the couscous and Basim the tagine, or Amina the tagine and Basim the couscous, but one and only one of them should accept the couscous. And otherwise, which means that if Amina and Basim are proposed, either they are both proposed tagine, or one of them is proposed tagine and the other one is proposed couscous, then in this case, they must order the same meal. Either they both order couscous, or they both order tagine. Okay, it's a little bit a mess, this game, but that's the rule. Okay, so again, let's do it slowly. If Amina and Basim are both proposed couscous, then only one of them, but only one of them should accept and take the couscous. The other one should take tagine. And if it's not the case, if we are not in the case in which Amina and Basim are both proposed couscous, they have to choose the same meal. Either they both choose couscous or they both choose tagine. Okay? Okay, I will keep these rules later in the other slides. But before, just a quick parenthesis. This is technical. This is for the one of you who have a little bit of background in logic. So this game is known as the, if I can switch, it's known as the CHSH game. So CHSH comes from Closer, Horn, Shimony, and Holt from the late 60s. And this is related to actually the separation of quantum computing versus classical computing. We will come to that in a minute. But in this game, we have these 2 players which cannot communicate. The player on the left, Amina, receives a bit, 0, 1, X. The player on the left, Basim, receives another bit, Y. And they should each produce another bit, A and B, respectively. They don't talk to each other. And the rule is that they have to produce the outcome, A and B, such that the exclusive OR of A and B is the AND of X and Y. I won't describe more. It's just for those of you who are aware of this type of logical notation. This is this apparently naive game in the restaurant. Actually, this is something very deep. We will see why in a minute. But that's the formulation. That's the mathematical formulation. But let's come back to our Moroccan formulation. So this is a Moroccan formulation of the CH-SH game. For today, it will be more convenient for us. So we have again Amina and Bassim. Amina is proposed either couscous or tagine. Bassim is either proposed couscous or tagine. They order either couscous or tagine, both, with the rule that if they are both proposed couscous, one and only one of them choose couscous. Otherwise, both of them should choose couscous, or both of them should choose tagine. Okay, so that's the game. So now let's try to play. Let's try to see if we can solve this game, if we can win this game. Okay, so here is, for instance, a table that Amina and Bassim could decide beforehand, before entering the restaurant. They decide, okay, Amina, if I am proposed tagine, I will take tagine. T is for tagine. And if I am proposed couscous, I will take couscous. The C is for couscous. Instead, Bassim, if he is proposed tagine, he will also take tagine, but if he is proposed couscous, he will take tagine anyway. That's what they decide, and they decide beforehand. So that's their algorithm, that's their rule. That's the rule that they will apply to the game. Okay, so let's see what's going on. If they are both proposed couscous, so we have to look at the right-hand column. If they are both proposed couscous, that's good, because Amina will take couscous, Bassim will take tagine, and that's good. That's the rule. If they are both proposed couscous, one and only one of them should choose couscous. That's good. They win in this case. If they are both proposed, for instance, tagine, that's also good. Both of them take tagine, so that's good. This is the rule. This is the second line in the rule. If, let's say, if Amina is proposed tagine and Bassim is proposed couscous, then they both take tagine, which is also good because the second rule says that they must take both the same meal. But there is a problem here. If Amina is proposed couscous and Bassim is proposed tagine, they will both accept their proposal. So Amina will take couscous, Bassim will take tagine. This is not okay. This is not okay. They were proposed two different meals. They did not agree on the meal they took. So they fail in this case. So it means that they don't win the game. They are not winning the game. This strategy, maybe another strategy would work, but this strategy will not allow them to win the game. They will win for some combination, but there is an offer in which they will always lose. The offer is when Amina is proposed couscous and Bassim is proposed tagine. So this is an example in this table that they will fail. They will not win the game. So maybe you would say, okay, maybe Bassim should also take couscous when he is proposed couscous. In fact, you will never succeed. For every such strategy that the two players or two players, Amina and Bassim, would choose, in any case, there will be always one combination for which they will lose. So we say that this game is not solvable deterministically. We already heard this term deterministic in the previous talk. So this is an example of a deterministic strategy. Here we call more about strategy than algorithm. So this strategy represented in this table doesn't work. No strategy actually can work. Deterministically, it's impossible. Okay, that's bad, but we can do a little bit better. So what can do Amina and Bassim? They can try to use sources of randomness. So what is randomness? Okay, what is randomness is a very, very philosophical question, and I won't answer this question here. But here for us, randomness will be just using coins, flipping the coins, and depending if it's head or face, taking different decisions. So we assume that Amina and tagine, not only they agree beforehand about the strategy that they will use, they also have, each of them has his or and her private coins. So Amina has a private coin, one or many coins, that she will flip so that to get some random input. And on his side, Basim will do the same with his coins. Now the question is, can they win the game using these coins? They will not win the game. Now it becomes a randomized process. It's like when you play lotteries. I mean, the question is, what is their chance of winning the game? What we have seen when it was deterministic, we have seen that there was, for every strategy, there was always a combination of offer by the waiter that they will lose systematically. Here we want to avoid this. We want that at least we have a good probability to win for each possible input, each possible offer from the waiter. So let's see what they could do. Well, there is a simple strategy they could do. Let's say one strategy would be Amina systematically accept the proposal of the waiter. If the waiter proposed tagine, she takes tagine. If the waiter proposed couscous, she takes couscous. Always. So she doesn't care, she doesn't use randomization. Her strategy is very, very simple, accept the proposal. For Basim, however, actually it's like if he ignored the proposal. He just flipped the coin. If the coin is head, he takes tagine. If the coin is tail, he takes couscous. So it means that the waiter can tell whatever he wants, can offer whatever he wants. Basim will just flip his coin and take the meal and order the meal according to the outcome of these coins. So what is the result of this strategy? Well, for Amina, she will always take what she is offered. Now, for Basim, what is the probability of being correct? Well, if it is the case in which they were both proposed couscous, Amina would take couscous because she always accepts, and Basim will flip the coin with probability 1/2. He will take couscous, so he will win with probability 1/2. And if in the second case, if they are not both of them propose couscous, then Amina will always take the meal she is proposed, and Basim will flip his coin. And with probability 1/2, it will take the same meal as Amina or a different meal from Amina. So he will also win the second bullet here with probability 1/2. So by doing randomization, they will be correct with probability 1/2. That's not so bad. It means that for half of the time when they go to this restaurant, they will not pay because they will win. So that's good. So is it the best we can do? The answer is yes. If we have what we call here private randomness, because each one of the two players is using its own sources of randomization, its own sources of randomness, each one is using its private coins, then in this case we can do some computation. It's not difficult to see that you cannot do better than 1/2. Okay, so that's already not so bad compared to before. Deterministically, it was hopeless. With randomization, they win with probability 1/2. They can do a little bit better by using a shared sources of randomness. Okay, so what does it mean? It means that instead of flipping their own coin on each on their side, privately, they will ask the waiter, please, flip the coins yourself and show us the outcome. So the waiter will flip the coin, show the outcome to Amina, and then go to Basim and show the outcome of the flipping to Basim. So it means that there is still randomization. The coins are flipped with probability 1/2 to be tail, 1/2 to be head. But now it's a common source of randomization. They see the same thing. They don't talk to each other, and there is no communication. It's just that they receive as part also of, not only they are proposed something by the waiter, but also let's say at the beginning, they are also shown the outcome of the random coins. And they see the same thing. So what can they do with this? They can do much better. So I will just tell you a little bit how. Think about this game. This game is essentially, there was a table. I show you a table at the beginning. There were 4 choices. There were, for Amina, there was what she does when she's proposed tagine, what she does when she's proposed couscous. And for Basim, it was also 2 possibilities. So in total, there were 4 possibilities. In fact, it gives 4 variables in equation that we call these things variables. And if you look at the equation, if you formalize these 2 bullets at the bottom of the slides, if you formalize them, you will also find 4 equations. So you have a system of 4 equations with 4 variables. And in fact, you cannot solve this system. This is why it's not solvable deterministically. But if you remove any one of these equations, which correspond to one possible input of the waiter, if you remove any one, then the system becomes solvable. So it means that you have we have 3 chances out of 4 to keep in the equation that correspond to the actual offer you were given. So the probability of winning the game, in this case, is actually 3/4. So this is, I mean, if you are a little bit more familiar with a little bit of equation, you can solve this system. Otherwise, believe me, they can win with probability 3/4. Very good, and you cannot do better than that. That's the best you can do. It's a little bit more complicated than before, but still not too difficult to show you cannot do better. Okay, that's good now. They can go to restaurant and with probability 3/4 they win. Could they do better? And yes, they could do better. But for this, they have to use quantum resources. So it will be difficult for Amina and Basim, but if they are, let's say, provided with quantum resources, they will do the game. So now instead of coins, instead of these coins that you flip, this will be that you can assume that they have some kind of, they share some entangled particles at the beginning, that they are in entangled quantum state. Now, in this case, I won't explain you at all what would be the result, what they could do, but if they are so well that they can bring quantum resources with them, then they will win the game with probability cosinus square of pi over 8. Who cares why is these values? But the important thing is that this is roughly 0.85, so which is larger than 3/4. So if they are using not classical coins, but they are using quantum resources, they will win this game with probability 0.85. Okay, that's amazing. Now they are close to really win almost all the time. Could they do better? Okay, now it becomes much more complicated. And actually it depends on in which world are we living. And in fact, this game, which looks very naive, that's kind of the core, it's the essence of the experiments that were used to demonstrate that we are living in the quantum world. It's maybe too much to say that, but that we are not living in the classical world. That is, if you take the equation of quantum physics and you create an experiment that looks a little bit like this game, and you can do this. This is, I mean, for instance, there was recently this Nobel Prize given to Alain Aspect. That's similar type of experiments. It's not easy to do, of course, such an experiment, but you can do an experiment that demonstrates that, in fact, in reality, in our world, the game is won with probability cosinus square of pi over 8. It's amazing how precise it fits with the prediction of quantum physics. This is what we can observe. So it doesn't necessarily mean that quantum physics is the truth, but it means that quantum physics, the theory of quantum physics, is in equation with the observation we can do in our world. So can they do better? Well, I mean, we believe, I mean, physicists actually believe not. It's not possible to do better. But now you see it's a little bit too difficult to model. I mean, what is this notion of, you see it's a little bit surprising because now I come to this notion of locality. They didn't talk to each other. They were sharing resources beforehand, but they didn't talk to each other. And still they are winning a game that is impossible to win deterministically. And they are winning it with a probability 85% of probability of winning. So it's quite big. So they are not local. I mean, they are far away, but still they can win the game very efficiently. So let's try to formalize a little bit what it means, these things. That's the things of when we transfer PowerPoint into this. Okay, so that's too bad the slide didn't show up properly, the previous slide. If we if we try to formalize private randomness and share randomness, we can formalize it and really determine that in fact the observation that resulting from physical experiment do not fit with the share randomness. We have to use some other notions of other distribution. And quantum physics, there are more correlation that appears between the two players. So in these slides, if you're not familiar with this, you don't need to read this equation, but this is a definition of what is non-signaling. It's a form of locality. So non-signaling, we say that a protocol with these two players is non-signaling, which means that they didn't exchange any information, the two players. They were really separated by this wall and they didn't talk to each other. It's non-signaling if and only if the marginal output distribution of Alice and Bob, so what does it mean? It means that you look at the game, the probability of the players to win, and you look at what happens, what is the probability for Alice and what is the probability for Bob. You kind of separate the two, that is what we call the marginal distribution. They depend only on their respective input. So it means that what you observe, if you observe the outcome of Alice, the random outcome of Alice, it doesn't depend on the input of Bob. It's only depend on the input to Alice. And the same thing for Bob. So that's the definition, that's the physical definition of being non-signaling. No communication between, no signal, no information are exchanged between the players. So the problem here is that there exists a non-signaling distribution that makes the player win with 100%. And this is a distribution that you have at the very end. Again, no need to really decipher what it means, but I just tell you that there is a distribution that is a distribution of the output of the two players that allows the two players to win with probability with 100, probability 100, probability 1, they systematically win, and still they are not communicating. You cannot implement this, I hope this animation at least, yes, these things will be correct with probability 1, but you cannot physically implement it because it is believed that our world is following the rule of quantum physics, and if it is the truth, the quantum physics, you can show that you cannot do better than this cosinus square pi over 8, which is 0.85. So you cannot do better, so you cannot reach these things. But in terms of pure communication, in terms of pure exchange of information, actually you could win with this game. if you would design a lower bound, trying to say, no, the complexity of this game is too high, they cannot win with probability 1. They cannot win with 100% of chance. You could say, if you use only the fact that Alice and Bob should not exchange information, then you will not be able to show this lower bound, because actually there is a distribution of outputs that satisfy that they win with probability 100%. It's just that this distribution cannot be implemented using the physical resource we have in reality. We can win with probability 85%, not with probability 100%. So all this discussion, all this little game was just to give you the intuition that defining what does it mean locality, what does it mean not exchanging information, what does it mean not communicating, it's very difficult actually to formalize. It's not something completely trivial. Okay, so in the second part of the talk, this is actually what you can do. This is a graphical representation of what is so-called Bell's inequality in physics. And in this picture, you have this, in dark gray, you have the things that are using classical physics, shear randomness, let's say. And they are limited, and you can solve, you have protocols that give you better results that are non-local, so that's the light gray area. And the quantum physics is between the non-signaling world and the signaling and the local boxes. So reality is in between complete locality, let's say, which is shear randomness, and non-signaling. It's something in between reality. Okay, so let's move now to distributed computing and to see whether we can use locality to show impossibility result or to show actually that we can solve a problem. So distributed computing is essentially a collection of autonomous devices that we call processes. I mean, they collaborate. They want to achieve some task. Like if we would be in this room, each one of us is one of these processes. And we exchange information, I don't know, through some communication medium. It could be the internet, it could be the network of a data center, or it could be the bus on the multi-core processes. And the processes, they may be synchronous, asynchronous, they may be subject to failures or not. I mean, that depends really on the models. I mean, in general, of course, you want to do the most general things. So you want to talk about asynchronous. If we are here running a distributed algorithm, each one of us, we run at our own speed. We can also be subject to failure in the sense that maybe one of us will be interrupted by a phone call, so we stop performing the task that we are doing together. So there are various notions of failures. Some of us may be malicious and wants the task that we want to solve together to fail. But that's the type of problem that people doing distributed computing are interested in. What I want to mention is that, of course, when you do distributed computing, you have a natural notion of locality. If you think about this little graph, let's say it's internet. It's a very abstract and simple representation of internet with the machine and the links between the nodes of these machines. And we can say, okay, node number one in one step of communication, let's say one round of communication, it can get only the information from its neighbors, node 7, 5, and 3. But it is not aware of what happened at node 6. Okay? So there is a notion of locality in this framework. Nevertheless, I skip this slide. Nevertheless, there are other systems in which locality seems to play no role. I mean, in this system here, I have a multi-core processes. The abstract representation is what we call shear randomness. Instead of communicating by sending messages along the edges of this graph, like we do in internet, you can assume that we have all these processes that reads and write in a shared memory. A shared memory is like a blackboard. You imagine that you have a huge blackboard and each one of us, we come and write on the blackboard. That's our way to communicate. We write on the board and we read what was written on the board. This is an abstraction for the shared memory. Well, so in this scenario, there is no notion of locality physical. Nevertheless, we will see that locality pops up in distributed computing. And for this, let me give you one short example. I skip this, and I want to show you only this example. In this example, that's a very basic case in which I have three processes, the white, the gray, and the black. And these processes, they are forming this network, this little network which is on the top right of the picture. This is just the white can send messages to the black and to the gray, but the black and the gray, they cannot communicate. So it's a very, very trivial network. Only white can send messages to black and gray. Now, on the left-hand side of the figure, there is what we call an input complex. This is the terminology we use. This is a representation, this is a graphical representation of all possible combination of inputs of these three processes. They can receive they could receive a 0 or a 1. So there are 8 possible combinations which are displayed as 8 possible triangles here. Okay? So that's each triangle represents one possible scenarios, and all these scenarios were grouped together, were glued together to form this kind of boxes, which is actually like a sphere. So we have this sphere with 8 possible scenarios, with all 8 possible combinations of zeros and 1. Now they communicate. So each combination of zeros and 1 at the beginning will give rise to another combination of knowledge after one round of communication. So for instance, let's say if they all start with 1, 1, 1, that's the top, it remains on the top on the figure on the right. And you see that the white, of course, remains with 2 question marks because the white didn't learn anything. But the gray and the black, they learn about the value of the white. So actually, it splitted this sphere that was a nice sphere, very well connected. It splitted into 2 that are 2 separated cones. So that's just knowledge. It's a representation of knowledge after one round of communication. And now, why is it interesting? Because now they could actually solve a task which is known as consensus. Consensus is one of the basic tasks. We want to agree on something. And we want to agree under centered rule that if we all start with 1, that means that we should agree on 1. And if all start with 0, we should all agree on zeros. That's the basic rule. Otherwise, we choose whether we agree on 1 or 0. But we should all agree. And the fact that we can split this sphere into 2 little cones allow us to solve consensus. Actually, it means that the upward cones, that's all the configuration that result after one round of communication, we can map it, they will decide 1, 1, 1, and all the bottom, they will decide 0, 0, 0. So by just this little slide here, what I wanted to represent is that there was communication in a network, but what was important is the knowledge that they learned. How much information did they get about the input of the other nodes? And if, thanks to this information, they could solve a task that actually you could show that you couldn't solve in one round, in 0 rounds. So you solve it in 1 round, not in 0 round. And this type of abstraction, and this will be my last slide, this is the general view of what people do in distributed computing to show impossibility results. And the first remark is that I use balls, none of them is a soccer ball. I wanted to be on the safe side because both of us, we suffer, we enjoy and suffer for the last World Cup, so I want to be cautious. So we have this representation here, we have the input complex. That's this little word, this little ball that I represent. It represents all possible input configuration. After a certain number of rounds, and it depends on the model, it depends on the time, it can be shared memory, there could be no physical notion of distances, there will be a deformation of this input complex into something which is more complicated, like this ball was cut into 2 parts. So this is a type of thing that happened so it's purely mathematical. We study the deformation. It's a topological deformation that depends on the model and the time. And then finding a solution means finding a mapping from these big things, this protocol complex, we call it, to the output complex. That's the general figure representing distributed computing. Where locality play a role here is that this mapping here from the top to the bottom, it should be what we call simplicial, which is exactly, it should preserve some form of locality. So it means that this topological deformation, what we want is that we run the algorithm such that starting from an input, at the beginning, there is a lot of uncertainty about the input of the other one because we don't know them. Maybe they are far, maybe they are next to us, but they are slow and they have not written on the blackboard. All kind of uncertainty about the other input. But if we run long enough, we will enable these processes to reconciliate and to learn more about the other processes. It will not decrease the uncertainty to 0, but still it will allow, to some extent, sometimes yes, sometimes no, it allows to solve the task. So if that's where pops up the notion of locality. If there is a way, after a certain number of certain time, depending again, the notion of time depends on the computing model. If after a certain time we can learn enough about the other processes, then maybe we have some chance that this mapping exists. Otherwise, if we can show that whatever is the time we use, there will never be such a function mapping from this gray protocol complex to the output complex, then it means that the task is unsolvable. And the structure here of these objects, depend on the model, could be very complex, but they have to do with locality. And in distributed computing, this is where locality here. Locality is in the existence of this so-called simplicial map. It could be physical, it could be notion of asynchrony, it doesn't really matter. The locality is captured by this type of topological deformation. And so to conclude, essentially, distributed computing is about resolving uncertainty by getting closer to each other perspective, as you have seen with the game with Amina and Basim. The measure of closeness, is difficult. It depends on the model, and the way we handle it in distributed computing is by doing this topological deformation, looking at the existence of these simplicial maps, because as you have seen, defining physical locality is something which is difficult, and in fact, the notion of locality we are using in distributed computing is slightly different. And with this, I think I have finished the slide. Thank you very much.